It is my pleasure to introduce Nick McKeown, professor of electrical engineering and computer science at Stanford University. Nick got his bachelor's degree at the University of Leeds in the north of England and his PhD at UC Berkeley under Jean Walron and Praveen Varaya. And then immediately got a faculty position at Stanford, where, as you probably well know, he has done a lot to transform the networking industry from the inside. He's had really groundbreaking research in what you do with buffers or without buffers. He's started 3 companies, all successful so far. The first one was Abrizio, which was sold to PMC Sierra, and then Nemo, where he was the CEO, and that was sold to Cisco, and those amounts were large but modest. And then he recently sold Nicira Networks to VMware for a lot of change, and a real landmark deal actually in the SDN industry. So Nick comes with many sorts of accolades. He's a fellow of just about anything you can be a fellow of, certainly the ACM and the IEEE, member of the National Academy of Engineering, the Royal Academy of Engineering in the UK. He has won the Kobayashi Award in the IEEE. And just last week in Helsinki, he was awarded the ACM SIGCOMM Award, which is basically the Nobel Prize in networking. And it doesn't mean Nobel Labs experience. It's all the greats have been award winners of the SIGCOMM Award. So please join me in welcoming Nick McKeown.
Thank you for having me here today. I've actually been to give a keynote at Hot Interconnects a few years ago, and so I thought I'd just finish off what I was saying last time. So we were interested at that time in the question of how big to make a router buffer, and it was work that had started with Guido Appenzeller when he was a PhD student, and Yasha Ganjali, who's sitting here, was also working on it. And we were kind of curious. In about 2003, we had asked about 4 or 5 different people why they think that router buffers were the size that they are. And we're researchers, so we're always looking for sort of interesting problems that weren't getting enough attention. And so all 5 people gave really confident, really kind of good sounding answers. The interesting thing was that they were all different. And the rule of thumb at the time was you need a bandwidth delay product of buffering in a router, and as you know, that's an awful lot of buffering when the line rates are high. And so the fact that they were all giving different answers kind of reminded me of that song, that line from that song, 2 men say they're Jesus, one of them must be wrong. And so we knew that not all 5 of them could be correct, and we became curious, why is it that the buffers were of this particular size? And so we started looking into it this time. So I thought we learned more after I gave the talk last time, so I'm just stealing some of my own time here to sort of tell you what happened towards the end of that. So the rule of thumb that's used by the operators is, and you'll know this RTT times C, right, the bandwidth delay product. And it came from some simulations that were done of an 8 node network about 25 years ago. And it kind of made sense at the time. When you're at a small network, this is probably the amount of buffering you need to maintain full utilization of the network. So to keep 100% throughput, 100% utilization of all the links. But as you probably, and you probably know that this comes from the TCP sawtooth. So it's essentially the distance between the peak and the trough of the sawtooth. It's the amount that you need to buffer to ride out the change when the window size is reduced. And the fact that it's a bandwidth delay product is purely an artifact of TCP. If TCP was to, instead of halving the window size, was to quarter it or a third it, then you'd actually need a different number. So it's purely an artifact of that. And there have been many papers published since then that say if you used a different congestion control algorithm, you'd need a different answer. So that was kind of curious. We became curious as to what would happen in a more modern network, and it turns out that if you've got sufficiently large number of flows, and you need quite a few of them for this to hold, for the desynchronization of the flows to take place, but this number reduces to bandwidth delay product divided by square root of n, where n is the number of flows in the network, and this turned out to be a very robust answer, a very robust sort of result, there was a number of router vendors, number of operators that took a look at this. And level 3 eventually took the plunge and said, okay, we're going to figure out how we build a nationwide network based on this answer, and ended up using routers that were using significantly smaller buffers. And it seemed very controversial at the time, and everybody's marketing departments of router vendors were paying people to try and discredit these results, and it was kind of funny. But my understanding is some people tell me that there are a number of WANs that run this way today, and the suggestion is based on the simple hardware that Google use in their WAN. Probably they use something like this as well. I don't know for sure. What happened after that, we were kind of curious as to what this would mean if you were to try and drive this earlier. So for a bandwidth delay product with a 10 gigabit per second WAN link, corresponds to about 2.5 million packets that you need to hold in the buffer. So this number goes down to 25,000 if you've got, say, 10,000 flows. It'll divide by 100, square root of 10,000. So that becomes a little bit more manageable. You can potentially then use an on-chip buffer, and smaller design, lower power, and so it provides some interesting options for the router. It also takes you into the realm of those boxes that are sold with 50% margins rather than 90% margins, so it becomes kind of interesting there as well. But so what happens when you go past this point? So this is me sort of completing the story from last time. So kind of quite interesting. If you've got a WAN link with a very large number of packets, you actually don't need a very large number of flows, but with at least a very large number of packets, the number of buffers that you need in order to maintain a high utilization drops off very, very fast. And the utilization begins to drop slowly. So up down to this RTT times C over square root of n, there's a very slow, up until that point you'll get 100% utilization. If you're willing to give up 5 or 10% utilization of the network, then you can drop the buffers all the way down to something that's closer to the log of the size of the window. It's a bit of a bizarre number. There have been a few different results that have reached a similar conclusion, similar sort of numbers. But the interesting thing is that this number is about 50 packets. So over here on the right-hand side, this area is determined by the aggregation of many windows. As you move down into this left, into the section in the middle, it starts to be dominated by the dynamics of a single window and the behavior of a single window and the burstiness within that single window. And as you go down into the left-hand side, it's the individual packet dynamics, which tend to be very smoothed if you've got a very large number of packets and a very large number of flows. It's not Poisson, we know that, but it becomes small enough that all the way down to that point, that last red dot on the left, it seems to hold a very high utilization, and then it plummets. And that curve on the left-hand side looks a little bit like what it would if it was an MM1Q or any of these queuing theory results. And the interesting thing is they don't depend on RTT, they don't depend on C, they don't depend on N, they don't depend on W. They purely depend on the size of the buffer. And so as you get into that, into that region down there. But the thing that was kind of fascinating for me was what happens, what does it mean that the technologies that you can use? Because we're down at the realm at that point of about 50 packets. Right, we're at about 50 packets at that point. There's this work that was done at UC Santa Barbara that some of you may have seen, that was first published by Emily Burmeister and John Bowers in about 3 or 4 years ago, where they showed that you could build an integrated optical buffer. And I always thought this kind of stuff was crazy and science fiction, and that it would make no sense trying to build a router with an optical buffer because you could never make the buffer big enough and you could never create a FIFO. And you know, I'm beginning to eat some of my own words here, because they began to demonstrate FIFOs that were made from an integrated optical delay line, but arranged as a FIFO. It was a true FIFO that would hold 20, 30, 40 packets. That's about as far as they've got so far. And it's getting to the realm of being kind of interesting. If you're willing to give up 5 or 10% of the throughput of the network, if you were in the all-optical domain. I'm not advocating going out and building all-optical routers, but since been noticing that a number of router vendors have been looking at this, so maybe this technology that seemed off-limits to us before is beginning to be kind of interesting. Anyway, I thought I would tell you about that. All right, so to the topic of my talk. So I think I was invited here because of the interest in software-defined networking, so maybe I better stick to that topic. But I want to start with a credit here. I'm the one standing here, but this is the guy that deserves all the credit. Many of you might know Martin Casado. He was a PhD student in my group at Stanford, worked with me and with Scott Schenker at Berkeley, and he was really the brains behind a lot of this, a lot of these ideas. Scott Schenker and Teemu were very involved in the architecture. Guru Parulka, who many of you know, working with my students at Stanford, many of them whom were very brave to work on this technology for their PhDs, even when it was unproven. And there's obviously been a lot of interest. And I want to just take a step back for a moment. Some of you may have heard me say what I'm about to say before, in which case I apologize. You can go to sleep for a while. But I just wanted to give a sense of where does this come from? What is going on here? And I was going to say that I think that it's totally inevitable. And if it wasn't called SDN, if it wasn't called OpenFlow, if there wasn't the Open Networking Foundation, this would happen anyway. It's just a trend that was inevitable. And it's the same thing that happened to the computer industry. So the computer industry in the 1980s, dominated by a single vendor, with a large number of smaller vendors. And with that one vendor, if you bought a computer, that meant buying a big mainframe. And that mainframe would have specialized hardware that came from IBM. It would have specialized operating system that came from IBM, and then specialized applications that came from IBM. And the general mentality was, if you want a network that works, if you want a computer that works, then leave it to us. That's what we do. We'll integrate everything and make it work for you, because this stuff is hard. Well, lo and behold, what happened was the microprocessor came along with a well-defined open interface. You can't build a microprocessor without creating an open interface. You have to publish the instruction set. And so that then made it possible for people to develop operating systems on top. And of course, there have been many. Many good ones, many ones that have flourished. And then on top of that, a huge number of applications. So an industry that was vertically integrated, closed, proprietary, very slow innovation, relatively small industry compared to what came later, turned into a horizontalized industry, open interfaces, much faster innovation, and a much bigger industry as a consequence. So the same thing is inevitable in networking at some point. It's just a question of when. Is it going to happen this year, next year? I don't know. It just is around about now, because we're in an industry where it's dominated by a relatively small number of vendors, where generally you're getting specialized hardware with specialized control planes, specialized features, vertically integrated into a single box. And what seems to be happening is that with the rise of merchant switching chips from Broadcom, Marvell, Intel, and others, that it's now got to a point, and of course they need to publish data sheets and they need to make available SDKs and APIs into those chips. The game is changing slightly, and many vendors already use merchant switching silicon, so this isn't news to anyone in the room, I'm sure. But as soon as that interface becomes more widely open, and particularly if it can become standardized, and today there's OpenFlow, but there'll be alternatives to that, I'm sure. And OpenFlow is a sort of a starting point for an interface to those switching chips. Then it allows the development of multiple control planes, so that you can have control planes that will control a large number of switches, and then have features that evolve on top and are developed maybe by the operator, maybe from the vendor, maybe from a third party, maybe open source, maybe closed source. Just suddenly gives lots of choice and more control to both observe and then modify the behavior of the network by the people who are operating it, and they, after all, are the ones that know how the network works best of all. So, a vertically integrated closed industry with relatively slow innovation. Change has been relatively slow in the network infrastructure. I think that what will happen is it will inevitably become horizontalized, open, and there'll be more rapid innovation. So where is this going to be? Where is this actually going to be deployed? Most of the discussion and hype so far has been about the multi-tenant virtualized data centers, both public and private cloud. So that's clearly where there's been a lot of interest. And that's largely because it's just easier. They're greenfield developments by people with deep pockets and a need to have low cost. They have very deep pockets. They have lots of software people, and so the idea of a software-defined network is very appealing if you're building a big public cloud. It will eventually find its way into the WAN. I'm not going to try and predict when that will happen. For any of you that have seen the descriptions of the Google WAN, we already know that their data centers are interconnected by an SDN network. And eventually it'll find its way into public WANs. We'll see when that is. In enterprise networks, people are asking for greater control, fewer middle boxes, the ability to determine where those middle boxes go, plumb traffic to them, rather than having to put them on the data path of the network. So ways of giving people more control over the way that they operate their networks. So you'll see it move into enterprise networks eventually. And I suspect that the ordering 1, 2, 3 is roughly the ordering in which you'll see it start to be deployed over the next few years. A little bit further out, I personally think, I don't see any activity in this area right now. Home networks for outsourced management of home networks. I think that's an interesting area. I would love to see it happen in cellular networks. If any of you have looked at cellular network technology, the networking side, it's like looking back into the 1970s. I mean, it's just shocking. It's just shocking. And the way in which they try and prevent innovation from happening by keeping all of the doors closed. Hopefully somebody will wake up and say, it would be much easier if I could run my network under my control rather than something that is so out of date. So I think this could allow for a separation of the service itself from the physical infrastructure, and we could start to see some very rapid innovation in cellular networks. I'm not holding my breath for this one. They've been remarkably good at keeping the walls very high and keeping innovation out, but we'll in the network side, but we'll see. Where it's already happening, so this is the ordering is wrong here, but in research and education networks, there are some national backbones for research and education and college campus networks that are starting to deploy this. If you're wondering what all of this hype is about and what the technology is, and just want to get your hands dirty with any of it, I would encourage you to, there's an online OpenFlow tutorial. It's actually more of a SDN tutorial. This is just the name that it has. So if you just do a search on your favorite search engine for OpenFlow tutorial, you'll find that. That's all freely available. That was developed by my students at Stanford. And then there's a network emulator called Mininet, designed with emulating SDN networks in mind. And it's pretty easy to use. A lot of people use it. It's actually used in the tutorial. Gives you a pretty high performance, so you can actually emulate networks. So it's kind of an interesting size. So if you search for Mininet, you should find that. So if you're interested in either you or someone that works with or for you trying some of this stuff out, it's a good way for you to draw your own conclusion as to what this technology is about. In terms of some of the support of these tools going forward, we recently set up something called the Open Networking Lab, and Huawei, our host today, is one of the founding sponsors of that. Thank you, Huawei. And it's an independent nonprofit lab that's set up in Palo Alto. And we're just hiring for that right now. So we'll be producing open source tools, and the idea is to help with deployments for people on college campuses for new interesting applications, and the open source tools primarily for the research and education market. It's based in Palo Alto. It's a great location and it's hiring, so send me your resumes after the talk. We'd love to hear from you. Okay, so where do I get these switches from? What's happening with the hardware? One of the most common questions that I get is, okay, this is all very well, but where is the damn hardware? Where are the switches? And so there's a certain amount of hardware that's available and switches that are available, and some people are aggressively doing it, some people are dragging their feet, as you might expect. And so this is, a snapshot of roughly what I'm aware of at the moment. There are software switches, of course. This is the easy part to do for the hypervisor switches in the multi-tenant data center. And some of you may be familiar with OpenVSwitch. It's now replacing the bridging software in Linux, so it comes as a standard as the distribution within Linux. And that has an OpenFlow spigot on the side in order to be able to control it. So that gives you control at the edge, which is a kind of a nice, interesting starting point. On the hardware switches, there have been announcements from a few vendors. Generally, you have to go and talk to them individually to find out what's really available and when it's available and what the pricing is. I stay out of that, but certainly HP, Brocade, and NEC have done so. Google clearly made their own, as they told us recently. You could go ask for one of theirs, but I don't think you would get one yet. In terms of switching ASICs, Current switching ASICs, they work with OpenFlow, but they're not really optimized for it. So OpenFlow was conceived to try and be feasible with existing ASICs, but to challenge them a little bit. And as you know, the ASIC industry moves very slowly. The chip industry moves very slowly because of the design cycle time. And so there's now developments going on. You should expect some within the next 1 to 2 years. Let me give you an example. We were kind of curious as to what's possible in silicon. So we've been working a little bit with TI Labs. We have a long relationship with TI from the days of Tiny Terra, and which was the first paper I ever published at Hot Interconnects. I just remember that, with TI back in 1995. And so we were curious. So they've been doing a design of an OpenFlow optimized chip, just using current ASIC technology. And I asked them whether I could tell you about that. And so they were happy for me to describe some of the details of this chip. So it's, as you might imagine, it's primarily a top-of-rack switch chip, and it's for a 64 by 10 gig design. And if you're familiar with OpenFlow, you'll know about this concept of multiple tables. So it will actually support up to 12, in fact, more than 12 different tables, but you can collapse any of them down into a smaller set. You could collapse them into 1, you could make them into 12. You can decide what functions, what lookups go in each of them. You're not restricted to have L2 first, then L3, and then L4. You can put them in any order that you want. There's 64K TCAM entries that are very, very wide, hundreds of bits wide for wildcarding, as well as 128K hash table entries, again, even wider for exact matches, so you can decide between them. You can take any combination of these, put them in any stage that you want. Supports well over 1,000 queues per port, with multiple levels of QoS, etc. All the OpenFlow counters, all the optional OpenFlow counters, has an on-chip ARM CPU and a generic ALU-based action engine, so you can define your own actions over and above the OpenFlow standard. I'm not here to try and persuade you should use this. It doesn't even exist yet. It's a design, and so this is work that we did with TI Labs. I'm telling you about it to give you a sense of there's no technical impediment to be able to do a chip which is relatively small, relatively low power, very affordable with technology today, which far exceeds the ability of the current switching ASICs for OpenFlow. You will have to come to your conclusion as to whether you think that will then happen, because then someone's got to put all the money in to turn that into a product. All I want to leave you with is it's perfectly technically feasible. It's just a question of whether someone's actually going to do it. My own personal belief is it will probably happen in the next couple of years, and we'll just have to wait and see. But if you're any doubt as to whether OpenFlow and SDN will be deployed in the WAN, you should go look at this talk, which was at the Open Networking Summit back in April from Sulzel at Google, and he was the keynote speaker standing here last year, and he gave a very good talk about the OpenFlow deployment at Google. So, as someone leaned over and said to me during that talk, the world just changed, right? Because suddenly OpenFlow went from this kind of academic-y thing into it's actually being deployed at scale. All right, so I want to get into a particular topic now related to SDN, of something that I think is not had much attention yet, for which I think it's going to be a very important aspect of SDN. And that is that as soon as we start to have a network that has this top-down control, which is being defined and then compiled down into the network, rather than a whole load of protocols that are all talking to each other, and then we're trying to figure out what on earth they're doing. So actually taking it the other way down, the other way around. I think it opens up some interesting possibilities for troubleshooting and debugging networks. If you saw me talk at the Open Networking Summit in April, then you're about to hear a repeat, and I apologize in advance, but I wanted to get this message across for anyone that hadn't heard it, because I think it's going to be a very important aspect. And when you're thinking about opportunities either for research or development, I think that there's some very interesting possibilities. And this is just generally in this topic of making networks work. Trying to define an intellectual framework for verifying, troubleshooting, and debugging SDNs. Okay, so this is mostly going to be a researchy discussion, but I'll try and give you a little bit of a background first as to why I think this is very feasible. It all comes from this belief that with software-defined networks, I believe that we can formally verify that our networks are behaving correctly in a way that we've not really been able to do before, that we should be able to identify bugs and then systematically track down their root cause. Now, this may sound just like an academic spouting, right? Anybody could stand up and say this. But there's something that's different about this kind of network, where you have a simple lowest layer that you're compiling down to, where you've got a well-defined instruction set for the network, from which everything that you're defining is compiled down. It gives you ways of checking that the behavior is actually as you intended. There's a whole bunch of papers about this, so it's kind of the lots and lots of papers coming out of the research community. I would highly encourage you to go read some of them. There's some really interesting ones coming from Princeton, from Berkeley. We're doing our own work, but there's groups all over the country and all over the world who are starting to do work in this. And I'll tell you why it's surprising in a moment that this is happening. So if you've got time to watch one more video, then you should definitely watch this one. This was Scott Schenker's talk from last year, The Future of Networking and the Past of Protocols. If you have an hour to spare, I think this is the best talk on network architecture I have ever heard. You may watch it and totally disagree with me, but I think that he masterfully described this new way of thinking of this sort of new networking abstractions that takes away from this disease that we have of thinking of networks in terms of protocols, of thinking that the network is defined by the protocol, rather than think it's defined by what we're trying to do, and then we compile down our intent. But instead, we think of, okay, how do we write another RFC in order to be able to define a new protocol and then introduce more complexity into the network? And then before we know it, we have 6,200 RFCs. So in this model, you've probably seen this picture before, you have a network of switches of forwarding elements, software or hardware, with a logically centralized control plane, sometimes referred to as the network operating system. It might be implemented through multiple distinct servers. And that network operating system is trying to maintain a consistent and an up-to-date view of the topology and the state of the network. So its job is just to present that to anything that sits above. And then on top, you may or may not have a network virtualization layer, which is then taking that physical view and trying to abstract and create different logical views for different features. So you might have different control programs that are doing various functions upon the network, and then that is a control program is a function upon that view of the network. So that abstraction is giving you a different view upon which you would write this function. So each one might have a different view of the network and a different topology that it's acting upon. Once we have this this kind of representation of the network. Let me give an example of, this is a Nick's very simplistic firewall program written as something as a functional view at the top. But forget about that this is a firewall, just think of this as any control program that you're trying to create. What the network will do is then eventually compile down that into a set of flow tables, and they're the match plus action flow entries in the switches. So through those various layers, it will take that program and then place it into the match plus action tables. So why is it that I think that we can or should or even care about producing tools that will allow us to verify and debug these networks? We all know that network management is considered a bit of a joke in the networking industry, right? It kind of doesn't exist. And so what is it? So why don't we look at some other industries and see what they do? How do other industries handle making their systems work? Well, the ASIC industry, as many of you will know better than I do, has developed this very rich tool chain Many, many different tools. I won't go through and describe them. I only know what half of them are. They are the sets of tools that allow you to have a high degree of confidence that the chip that you're about to make actually is what you intended. And it's operating at multiple layers. It's operating in multiple independent ways, giving you different views. But because of the cost of making a mistake is so high, we now have a roughly $10 billion tool business supporting a roughly $250 billion chip business, right? In the academic sphere, you can find hundreds of books on the topic. Even a quick search on Google Scholar, you'll find way over 10,000 papers on this. It's probably way more than that. There are tens of classes that you can take at universities, all on this topic of how do we make ASICS work. Same goes for software, right? There are many tools, there are many ways. It's probably even a greater variation of approaches for software engineering. There's a big tool business. It's about $10 billion tool business supporting a roughly $300 billion software industry. There are hundreds of books, right? Just go into a tech bookstore and you'll find there are hundreds of books on these different things. There are well over 100,000 papers, research papers that have been written on the topic. You can take tens of classes on these topics. So what do we have as the networking industry? It's pretty much what we have, right? So compared to those $10 billion, we have traceroute, ping, tcpdump, and SNMP and netflow. They're pretty good, but it's kind of pathetic when you compare it to the job that is at hand. What is it that we're trying to solve? We're trying to make really, really significant networks upon which we all depend with a very rudimentary set of tools. So it really is about it. So what is it that makes networking, debugging a network so hard? What is it that makes it so hard? There's this complex interaction between multiple protocols sitting on a box, and then between the state that they have then inserted onto all of those boxes, all independently of each other, on different switches and routers. So you've got all of this state distributed across that's all put in by different writers of that state, all operating independently of each other. So as an operator, you can neither see all of the state nor control all of the state. So you're trying to manage a huge system for which you can neither see nor control the state. That kind of seems like a recipe for disaster, and it's amazing that networks work to the extent that they do, and that they're really kind of held together by these, as Scott Schenker put it, these masters of complexity, right? These people who have been doing this for years and years and years, who have developed this into an art form of being able to keep networks working. Now that's fantastic, and it's great that people around us like that, but it's not very scalable. And if you look at it at the academic point of view, I actually found it hard to find a real network management book, right? I mean, there's a couple of them. There's almost no papers. There's no classes. It's not a discipline, right? It's not considered a discipline. And sorry if you've seen this joke before, but I think that the philosophy of making networks work is kind of like a yo-yo, which is you're on your own. Right? And we're kind of left by the equipment vendors to be on our own to run a network, to figure out, and everyone's developed their own scripts and their own expertise. They're firing off trace routes and pings and trying to figure out what the network is doing to try and observe that state so they have some clue as to what's going on. And they're incredible pattern matches for, oh yeah, I saw this particular bug 5 years ago, therefore I can tell that it was this box over here that was probably misconfigured. I always like to say in England, we actually call it yo-yo ma, because that stands for you're on your own, mate. So, to get back to the message, I think that we can formally verify that our networks are behaving correctly, identify bugs, systematically track down their root cause. So I've told you about why I think we should try and do it. Let me now try and tell you about one possible way in which we might actually be able to do it, or at least one piece of that solution. So the software infrastructure that sits on top of this forwarding plane, there are many places to have errors, right? It's software, and it's software written by humans. It will have bugs. It will have errors. So our control program is where we start, but the most code is going to be in that software infrastructure in the middle. So right in the operating system and the virtualization layer, on top, the control program that we write might have bugs in it. There may be an error in the middle that causes so we might have a program that's correct, but it might be compiled down incorrectly when it's put into the flow tables. There might be hardware errors in the switches themselves that causes them to malfunction. There might be failures on the links. There are really sort of 4 broad categories of place where things can go wrong. There's been some great work done from Princeton and from Cornell on how you can write those control programs in constrained ways so that you're very unlikely to make a mistake when compiling the program in the first place. So there's some interesting work. It's beginning, and there will be plenty more of that kind of work, I think. Some of the work that we've been doing has been taking a slightly different view of how you might independently, statically check the contents of those flow tables, and that's an example I'm going to show you in a moment, or how you might automatically generate test packets that will maximize the chances of finding an error if there's a hardware error in the network, and some interactive debugging tools for finding the kinds of errors that the other tools won't find for you. So I think I'm only going to have time to talk about one of them. All 3 of these have been recently written up. I'm not going to describe this as we have the answer. That's not what I'm here. I'm here to say we're just beginning to scratch the surface. I think that there is a huge potential here, and I would encourage you to read these papers and think about what other things can be brought to bear, because I think that just like in the ASIC industry, when it all started up, there was probably 4 or 5 people thinking about it, and before long, there were thousands of people bringing massive innovation to the problem of how you design a chip correctly. So this is the one that I'm going to be talking about. This is work that was done with 2 of my students and George Varghese, who some of you may know from UC San Diego. So this is on how you might do static checking of the correct behavior of the network. So I like to say that in today's networks, it's really quite hard to ask quite simple questions. Things like, can I be sure, viewing from the outside, that A can talk to B? Or that, can I identify all the set of packets that A could send that could reach B? Not obvious how you would do that in the network today without actually going and sending all possible packet headers and seeing what could reach B. Are there any loops in the network that either are loops within a particular protocol or loops that go through multiple protocols, as we found on the Stanford campus? Can I provably say that group X cannot talk to Y? So if I'm on a hospital network, can I say that medical provider A can't talk to medical provider B, and prove it? And prove that as a property of the network. So you imagine doing that with the networks that we have today. It's a little bit hard. What happens if I go into a config file and remove an entry? What will be the consequences on the network? Can I tell in advance whether I will introduce loops, whether I will prevent A from talking to B, things like that? How do I determine what the consequences will be of making a change? We were told in a survey that the primary reason that config files stay the same for a long period of time is everyone's scared to touch them because the person that put in that entry has now left the company. And so they're not quite sure why it was there, and they're not quite sure what will happen if they change it. So being able to then modify the behavior and see what the consequences will be seems quite interesting. So you could think of the flow table state as being a little bit like the machine code of the network, right? It's the assembler of the network. It's what's defining the operation on each on each packet. So we were wondering, could you create a tool that will sit outside the network, so it's outside of this stack, independently observing what's in the tables and seeing whether what they're doing makes sense? So rather than putting this in line with the vertical software stack, there would be value to having something there as well. But independently from that, having something that sits on the outside and say, can I see something that's actually kind of bad behavior? So this would then read and sort of slurp up the contents of the flow tables and the switches, and they would have to have some rules that it's checking against, which could be, grandiosely called a policy. It could just be a set of objectives that you have for the network, or a set of questions that you ask of the network in an interactive way. So think of this as something that's observing on the outside. Okay, so the way in which we, I'm going to tell you about one way that we implement this. It's with this thing called header space analysis. And I'm going to explain what this is. And the reason I'm going to explain what it is because we've come to the conclusion afterwards that this method is probably usable in many other ways other than just this static checking. And for those of you that have read papers on packet classification in the past, it's going to be very familiar because it borrows many of the ideas from that, but we actually think that there's a sort of a more general way of thinking about this. So I'm going to tell you what this thing, header space analysis, is, and then I'm going to try and explain why I think that it will be a valuable way to think of how you analyze the way in which a network behaves. So consider this network here. it's a very simple network with A on the left and B on the right. And we're going to consider packets in this network as having a data portion and a header portion. And that header portion, we're just going to assume that there is some maximum length header. We'll just say it's L. Doesn't matter what L is. And that header can take on any value, any bit string. So of all the 2 to the L different values. And we can represent this in an L-dimensional space as a point. Right, the L dimensions representing each of the bit positions in that header. So just an abstract view of what a packet does, of what a packet is. So for those of you who've seen papers on packet classification, this is usually done by fields, multiple fields in different dimensions. Which is to say, we're not going to think about what the network is, what IP is or what Ethernet does. We're just going to say, every packet will have a specific value. It must have a value of a 0 or 1 in any of those bit positions. And as it goes through the network, the switches and routers will operate on that header, potentially change it and modify it. It might pop or push, might change and overwrite a value, but it's going to operate on that header. Okay, so here's that L-dimensional. I can only draw 3 in PowerPoint. That's that header as a point in that space. And as that packet goes through the network, it's going to be moved around on that point. It might actually stay in the same location if the packet isn't changed, but it might be a checksum that's changed, a TTL that's decremented, or it might be a NAT box or something like that causes it to be changed. We're just saying in general it can change. If we include then the port ID of all the ports in the network and include that in our space, so we've got the space of all headers cross-producted with the space of all ports, we can then put these on a line that says amongst all the ports in the network, you can sort of see how it will be transformed through all of those ports. So you can say one packet will have a trajectory through all of those, corresponding, say, from A to B, as going from starting at one point, going on through a sequence of points until it reaches B. So that packet will be transformed. Okay. So if we look at from the perspective of a packet entering at that red router on the left, it would be transformed maybe onto a particular outgoing link. And then if we then go back and say, while that particular point may be transformed in that particular way, there will be a collection of other headers that will be transformed in an identical way. So there's actually a space, a collection of headers that will all be transformed in a similar way. So for example, if we say this region of headers shown as this prism here would all be mapped into this prism on the right, right? So they'd all be mapped in the same way. So now we're able to treat all of the packets within that region exactly the same and figure out a transfer function that corresponds to that region. So it is essentially a geometric problem. So it's turning the processing of packets into this geometric problem. And we'll see later why this is why this seems to be quite powerful. And so you get a collection of these geometric functions through the network, and you can actually represent each of the switches or routers as a transform function on that geometric space. So the match plus action rules in the tables are really just transformers of that space. And in fact, so is a IP forwarding rule in IP prefixes as well. So you can represent the way that we use networks today in this way as in this way as well. So once we have it as represented as these transform functions, we can then combine them, and we can say things like I can ask questions of can A talk to B by looking at the transform of all possible packet headers. Imagine that they were inserted at the left. What happens to all of those packet headers as they go through the network? Well, that would be transformed here by the first box, transformed like this by the second boxes, and then ends up with these two regions over here. So that would be the region. Now what I've discovered is that if I send any packet from the left, these are the only ones that can show up on the right. Okay? Now imagine that I go backwards, invert all of the functions, go back through the network, and find out what are the set of packets that could have led to this set in the first place. So if I take what reached, do the inverse function all the way back to the beginning, I can find out eventually these two purple boxes. These are the only packets that A could have ever sent that reached B. Right? So I now know all of the sets of packets that A can send that can reach B. They're the ones inside those purple boxes. There are no other packets that it can send that can reach B. So I haven't mentioned IP, I haven't mentioned L2, I haven't mentioned L4 or whatever, right? It's all in terms of the transfer functions represented by those flow entries in the switches. The consequence of this turned out to be really kind of interesting. Essentially it's creating an abstract forwarding model, right, which is kind of what OpenFlow does. It creates this sort of abstract forwarding model that says this match plus action is what a router does. It's independent of the protocol, because it doesn't have encoded in it some meaning of the fields. You can do things like find all of the packets from A that will reach B, find loops regardless of the protocol layer. You can prove that groups are isolated from each other. And so to some extent, you can prove that a network is adhering to its policy just by examining the forwarding rules in the network. So there's a paper that was in NSDI earlier this year that describes this method for doing static analysis of networks. Okay? But actually, we think that there's more that you can do with this. It seems like a little bit of a sort of a foundation upon which you can build other things. That should say HSA, not HAS. So HSA enables, we think, many tools and methods. Independent static checking, as I just described. So you could also put that same thing into the vertical software stack, so you check every rule as it's being added into the network to see that it doesn't violate an invariant property of the network. So you could put it in line. We've also used it for automatically generating test packets. So you can say, how can I test that all of the switches in the network are behaving correctly? In other words, they're doing what the flow tables say that they should. How do I generate a set of test packets that you could send in, the minimum set that you would need in order to be able to test that behavior? And the numbers turn out to be quite interesting. You can send in a very small number of packets, and you can determine what the minimum set is in order to be able to find that one of the rules is misbehaving. So there's a kind of an analogy here to Boolean algebra, I think, for logic design. It's a method. It's a sort of a base method upon which you could then build other things. So we built a tool for this, and it's available on open source if you'd like. The link is at the bottom of the slide here. I'll post these slides afterwards on my website at Stanford, so if you don't get to write this down. What we did was you can do a certain amount by reading configurations from switches and routers today. You can't do very much, but you can do certain things in terms of reachability testing. You kind of lumbered with the CLI or whatever it is that's on the box. But by taking the Stanford network and then saying, can I figure out all of the sets of packets that can go between two pairs, checking a set of policies. There's a Python program you'll find here that will take about 10 minutes of a network of that size. It's a 35,000 people network at Stanford. And in C, it's a very parallelizable problem, so you can, it will do it in about 60 milliseconds. So we think that over time this will get faster and faster, and you can start to do this in real time as you're adding new rules into the network. So it means that you start to build these tools and these methods that will give a prove and check and check that the network is doing what you intended. There's work that we've been doing on interactive debuggers that try and emulate the behavior of something like GDB. That will try and give you a backtrace of the network behavior to try and figure out what offending line in your control program actually led to that's work that we have ongoing at the moment. If anyone is interested in providing us with test cases or failure cases, sort of interesting examples of when networks failed, you can help us to help you, because by giving us examples that you have, it allows us to try and come up with tools that will be useful back, and we always make these available for free, and we always give them away at the end. I'm going to see whether this works. I've lost my mouse. All right. What I was hoping to do here. Can anyone see my? Oh, there it is. Okay. This was supposed to be a little easier than this. Okay. So I started out by saying that I think that we'll be able to formally verify networks, and I think this is, we're just entering a time when we'll be able to do this. And this really comes from, in this software-defined networking layers of abstraction, it really does allow for a stronger intellectual foundation to networking. I may sound like a head in the clouds academic when I say that. I don't mean to say that there's something silly about what we do today, but where we got to today was in a little bit of an ad hoc way. There were some brilliant ideas that led to the original creation of TCP/IP to allow for this very, very rampant organic growth. But it seems like it's a time that gives us the opportunity to say you can do all of those things, but now you allow the operator to have a little bit more control over what the network does and over how each of those layers actually are implemented to allow for ideas that are over and above, that are in the interest of the operator rather than just the vendor. So it allows us to define solid abstractions and to reason about those abstractions. And I really do think that it'll allow us to transfer technology much faster in both directions. One of the things that I've always admired about Hot Interconnects is one of the very few workshops and conferences that are right at the boundary between the practice and the research. There's very, very few networking conferences, I can't think of any others, for which there's such a rapid transfer in both directions. There's an exchange of ideas, there's an exchange of problems, there's an exchange of technology that goes very, very healthily in both directions. And I think that SDN will accelerate that. That's why I wanted to talk about it here, because I think that it can even help accelerate that within this community as well. And I always think about trying to close the gap between academia and industry, and I think that this provides an opportunity to do so. Thank you.